Hello everyone, and welcome to our S5 video. Today we'll be talking about one-hot circuits. So what is a one-hot circuit? Well, basically what a one-hot circuit is just a circuit that always has one of the flip-flops outputting a high value. This helps to shorten propagation delays, which can be a big help when creating circuits like this. So going into what a design process looks like, we first start off with our state diagram. And our state diagram looks a little bit different than what we typically see because of these 0B, 25A, 25B, 0A, 50B, and 50A. So these A's and B's are states where the coin will be held into the problem. So basically what our goal today is, the state diagram, is to create a vending machine that inputs a nickel, and every time, or once this nickel reaches 10000 or 0A, it'll dispense out a gumball. So starting here, you see that we have our 0B, so if we don't input one, it'll stay at 0B. If we insert a quarter, it'll go to 25A and it will hold there. So when this value is still holding, it'll stay at 25, and then you put it in, or then so once that lever, so you go in and it hits a lever here, and this lever will stay held at 1 until the lever is released, to then which it will go to the next one, and the lever will be pressed. Next quarter goes in, lever pressed, lever will stay, lever is released, and then on the 75 cents, when the lever is released and the cent is going in, that's when you will receive your gumball. So looking at our state table, again, pretty simple, pretty straightforward, but you'll see by our state diagram we actually have 6 binary bits, which helps us to create 6 flip-flops in our design process. So this is what the state diagram is showing here. And here is the remaining our J and K values, since we went ahead and used J and K flip-flops for this design process. So once we started taking a look at these tables, we derived our Boolean equations. And you can see here that these equations follow a simple pattern. Every single time that a flip-flop is turned on, we have our Q0X here, which means the lever was pressed, but we also need to turn that lever off. So we're going to go ahead and use that same equation that we have to turn that lever off, which you can see here is a common theme. So J2 is K1 or Q1X prime, and to turn it off, we're going to do K1 as Q1X prime as well. And the pattern continues forward. To kind of show you guys what I mean, I'll go ahead and show you guys my Logistim circuit here. So to go ahead and start, we needed our initialized value, which means we always needed to keep one of these high to start off to initiate our circuit. And so if we go ahead and run this, you'll see. So if we just do this frequency, kind of lower the frequency here to make it a little easier to see. So as you can see, it jumped to our second state here. But you see that as the clock's turning, it is actually still staying at this thing, and that's staying at this state because the lever is actually still pressed. But once this lever is released, it'll go ahead and actually jump to the next state. And as you can see, this lever is not moving. The lever has now been released and is waiting for the next entry, or the next positive value, I should say, or quarter in this problem that we have today. So if I go ahead and turn this on, it's on this next positive clock edge, goes to the next state, turn it off, goes to the next state, and on this last state here, once we enter in once we enter in a value, we should dispense a gumball, which will flash red right here. As you can see, it flashes red and then turns off again, and then we'll reset back to where its original value. So in a whole, that's pretty much the entirety of the circuit that I have today. And the reason that these held inputs, like I discussed earlier, are so important in terms of real designs is because once that lever is pressed, um, any values can kind of pass in and out of it without it causing any problems until that lever is released again. Also, if we wanted to, we could also make this clock go super fast. So if I go ahead and put it at, 8 hertz and go ahead and run this, this will run incredibly fast. And as you can see, it cycles through very fast, and the light only flashed red very fast. So I can show it, but keep your eyes on this gumball here, and red, and then turns off. So super fast, super quick, but the clock can run at any speed that it wants to. It doesn't really matter. As soon as it hits that 10000 value, it'll go ahead and change, give you your gumball. And that is all I have for you guys today. Thank you.